Welcome to Topology Lesson 6 concerning the classification of surfaces. We're going to talk about a classification theorem for closed surfaces. Surprisingly, there's only 3 cases that cover everything, and if we're a little bit clever, we can actually reduce it down to just 2 cases. A closed surface contains a volume of space enclosed from all directions. It consists of one connected hollow piece that has no holes and does not intersect itself. A closed surface is one without a boundary, such as a torus or a sphere, but not a cylinder or a Mobius strip. That would also exclude the Klein bottle, which it has no interior, so it doesn't include a volume. But it's true, it doesn't have a boundary either. So just a note here, the word closed is used even in math different ways. And this lecture series, we're going to get into metric spaces and topological spaces after this lecture. And the term closed is used differently there. So just as a warning for things to come, that we're using the word closed in different ways. Not my choice, but it's the way things are. So we have a theorem here. Closed surfaces are classified as follows. Each two-sided orientable closed surface is homeomorphic to n toruses connected together. So we've seen this notation before. It's just the notation T for torus and number n for the number of tori connected together. And then if you want to take the case n equals 0, which we also mentioned before, but you don't have a torus, but you have a sphere, then that can be included in this notation here, I guess you would say. So if you have a two-sided orientable closed surface, it's one or more, or 0 or more tori put together, connected together. And each one-sided non-orientable closed surface is homeomorphic to one or more connected projective planes. So this is why we spent some time on tori and projective planes, because they're the important pieces that allow us to classify all closed surfaces. In one case, we cover the orientable surfaces, and in the other case, we cover the one-sided non-orientable closed surfaces. The previous theorem comes from a book on topology by Earl. I have the reference in my book, which you can download. Earl goes on to make a statement here, which I'll read through quickly. I did mention some of this before, so just reiterating here. Making a connected sum with P, the projective plane, is equivalent to sewing a Mobius strip into the surface. P itself can be made by introducing a Mobius strip into a sphere. And that was where we talked about the cross cap in the previous lesson, where you make a tear and then twist the two sides of the tear together in a rather complex way to get a cross cap. And once you have that, you can think of the surface P hash K can be thought of as a sphere with K Mobius strips sewn into it. So that's just reiterating some ideas we discussed previously. The Klein bottle, which isn't in the theorem because it's not a closed surface, but it can be represented as the connection between two instances of the projective plane. That's a fact. And then for a more detailed yet basic presentation, there's an unpublished paper entitled Classification of Surfaces. And again, this reference is in my book. I would encourage you to download that if you're interested in more details. So I'm repeating myself a bit here, but I thought it'd be useful just to hammer home the point. So the classification theorem of closed surfaces states that any connected closed surface is homeomorphic to some member of one of the three families. So as we mentioned, the sphere can be seen as a torus of where you have the connected sum 0. In other words, there's 0 tori when you so you have nothing to connect together, and you can look at the sphere as being that case. Then we have the connected sum of one or more tori is one case, and the connected sum of k real projective planes is the third case. And as we mentioned previously, the surfaces in the first two families are orientable. It is convenient to combine, I already said that you can combine these two cases by thinking of G being 0, and that takes in the case of the sphere. Yeah, the number G of the tori involved is called the genus of the surface. The surface and the torus have Euler characteristics. The sphere and the torus have Euler characteristics 2 and 0 respectively, and in general the Euler characteristic of the connected sum of G tori is 2 minus 2G. So we had that in the last lesson, just repeating or re-emphasizing some things. Then the surface in the third family, as we know, are non-orientable. The Euler characteristic of the real projective plane is 1, and in general the Euler characteristic of the connected sum of k of the projective planes is 2 minus k. And remember, we also, instead of saying genus, we used the term non-orientable genus, and that was the number of cross caps in this case here. So it follows that a closed surface is determined up to homeomorphism by two pieces of information: its Euler characteristic and whether it is orientable or not. In other words, Euler characteristic and orientability completely classify closed surfaces up to homeomorphism. Okay, so that's the lecture on surfaces. Rather short, just a few lectures on this, and the topic, you can write a whole book on it. So I've given you some references. Hopefully you can follow up on those if you're interested. This is not the end of the video series on topology. We're going to have several lectures on metric spaces, which is kind of a more general way of talking about topology, where you have a distance function. And then finally, the last set of lectures will be on topological spaces, where we remove the distance function, and we're still able to define a topological space, an entity that has open sets, and the metric space is kind of one example of a topological space. Some books and lectures go in the opposite direction. They'll first talk about topological spaces, and then somewhere in the discussion they'll mention a sort of a special case of metric spaces. But I decided to kind of give you the more concrete thing first, which are the metric spaces, and then go on the topological spaces. So what you're going to see next is much more abstract than what we have here with the surfaces, which you can kind of visualize and get some sense of. But the metric spaces and topological spaces, while they have some specific examples, the general theory is quite abstract. Okay, so I hope you decide to continue on with this series, and talk to you soon.